All right, I think we can start. Thank you everyone for coming. I'm David. I'm a solution architect at Couchbase. Couchbase develops a NoSQL database, kind of like MongoDB, which probably you've heard of, but not really. Much better, obviously. That's not what I'm actually going to talk about today. It has nothing to do with databases. We're going to be talking about processing streaming data, a lot of it. I'd like to point out that there's only one person brave enough to sit in the front row, and I salute you for that. And the rest of you obviously should feel shame. All right, so before we start, right, I like to do a little quiz to see who we have in the room. So how many people here write code for a living? Everybody. Who doesn't? Who does something else, like managing or architecture stuff? Nobody is willing to admit to managing. All right, good. So who writes code in .NET? It's like, again, everybody. All right, how about Java? It's like 5 people. All right, well, this is going to be a tough crowd because I do have a lot of Java examples, and I don't say I didn't warn you. How about JavaScript? It's like half the room. I don't know what you guys are doing here, honestly, but all right. Okay. Anything weird and esoteric, like PHP, Python, Erlang? All right, cool. So anyway, we're going to be talking about streaming data and processing it in real time and getting interesting stuff out of it. But obviously the first thing is, why do we even need this stuff, right? And we can always write an application which listens to a queue, does something, and puts it in a database. And this is basically like 95% of applications in the world. That's basically what they do. They listen for incoming messages, do something with them, and put them in a database. So when I say streaming data and processing data, first of all, what I mean is at large scale. And when I say large scale, let's say, who knows how many tweets happen every second, approximately? Let's look at 100. Who thinks it's 100? Nobody thinks it's 100. 1,000. How about 10,000 per second, mind you? Per second. All right, 20,000. 100,000 tweets per second. What? No, it's more like 6,000 per second on average, which is like 500 million a day, which is a lot of data. And if you consider that every tweet comes with, it's not just 140 characters, right? It's actually a lot more. There's metadata and all that. It's a lot of data to process in a single day, and even in a second. But tweets aren't actually a lot of data. How many Google searches happen every second? 10,000? 100,000? 1 million Google searches every second. Like no one's willing to raise, because I confuse everybody, screw this. No, it's more like 50,000 per second Google searches, that's a lot. Let's go higher. YouTube video views. How many YouTube video views? 10,000. No one's willing to actually play this game anymore. All right, I'll just tell you. So it's around 100,000 YouTube views per second. And when I say views, you have to think about what actually happens when a user goes and does a Google search or does a YouTube video view, or goes to a website that you guys built, and assuming you do some kind of metric collection or user tracking and a bunch of stuff, every visit actually is a lot of operations in the background, right? It's going to generate a bunch of user interactions with the website, which you probably need to record somewhere and eventually probably process and show ads to the user, because that's what the internet is basically about. And every one of those causes a whole chain reaction of different things that you have to process. So a single tweet is one event on the front end, but it's hundreds of events on the back end that you need to process. You need to find all the users who follow that person and update their feeds, and you need to do some processing to discover trends and separate out the hashtags, and there's a bunch of stuff. And by the way, I'm going to keep going back to tweets because it's just very convenient to talk about tweets in a streaming context, but you can just mentally map this to pretty much any domain you work in, whether it's doing fraud analysis or online shopping or whatever. You can pretty much think of it in terms of events coming in from some kind of edge, whether it's a device or a website, going into your backend server system, doing some kind of processing with them. And the reason I'm talking about streaming data is because not all data is created equal, right? Data loses value very quickly, right? If you're going to be monitoring, again, for example, tweets, if you have a startup which does social network monitoring, there's like 100 startups that do this, right? And they create alerts and possibly, change bids on ads or do some kind of stuff in response to social media events. The difference between doing it a second later or an hour later is huge, right? So data actually tapers off and loses value very quickly, which is why we actually want to process data in real time for a lot of applications. And again, doing this at scale is very difficult, and there's a lot of different tools, which I'm going to be talking about throughout this talk. So in general, stream processing can be divided into a couple of things. And it's not new, right? Stream processing actually has been around for a couple of decades at least. It originated as complex event processing, mostly in the stock market, where there was a lot of need for analyzing trends and aggregating different data, merging different stock feeds, and trying to predict what to do with stocks. And that kind of complex events processing was very expensive and very time-consuming. But modern applications don't really need that kind of complexity, so we have a whole separate domain which is simple stream processing, where you have events coming in, you have to do something very simple with them, maybe update a database profile, or maybe run some kind of process in the background as the response to that event, and then you forget about it, or you write it to some permanent storage. So these two worlds, they're kind of close together, but they're actually separate, and I'm mostly going to be talking about simple stream processing, and we'll talk a little bit about complex event processing a bit later, because the tools used there are different, and they're kind of outdated, so it's not very interesting for this talk. So let's talk about the types of data processing you can do, right? And when we talk about data processing, we can easily talk about the throughput of how many things you can actually process per second versus how quickly you can process them, right? And if you think about something like a database, right? Databases, we expect them to process hundreds, maybe thousands of events per second, queries and transactions, and we expect latencies in the second or 10-second range. And if you want to do something much more high scale, you go to NoSQL databases or in-memory databases where you can process hundreds of thousands of events at millisecond latencies. And the higher you go into memory, you can process things quicker, and it becomes much more expensive and much more volatile because keeping things in memory is not as durable as keeping them on disk. And if you go in the other direction, you talk about things like Hadoop and Spark. How many people have actually heard of Hadoop and Spark? Pretty much everyone. How many people use that in their company, not necessarily yourselves? It's like, no, you've heard of it, but no one except one person is using it. You have no Hadoop or Spark or any kind of data processing in your organization at all? Excellent. You'll learn a lot of new stuff today. All right, that's actually good. So the kind of large-scale batch processing, which we expect to take minutes or hours, but then we expect a very large volume of processing, right? If you have to process a petabyte of events or a petabyte of data, it will take a long time, but that's what we have batch processing for. And real-time processing is on the opposite scale of that, right? We want to process events as quickly as possible, and obviously at a high scale as possible, which kind of conflicts with each other, right? So higher throughput means we will take longer to process every event. So let's talk about what we can use for that, right? And there are a lot of open source frameworks which can do all of this. Hopefully you've heard at least the names of some of them. Spark, has anyone heard of Spark, Apache Spark? There's like half the room, which is good. And there's a bunch of others. There's Apache Storm. All of these projects have the names starting with Apache something, right? They're all open source projects, all of them JVM based. We'll get to Microsoft stuff in just a moment. There's Flink and Kafka. Kafka, I'm sure everyone's heard of Kafka, right? It's a message queue. Okay, don't have to raise your hands, that's fine. All right, and so Storm, and each one of those actually does something somewhat different, and so it's interesting to think about, not just about frameworks, because the frameworks themselves, there's new frameworks coming out every year, and old frameworks die off, but the concepts each one implements are very interesting, even if you're going to go and roll your own, which I don't recommend, but if you're going to roll your own framework, it's important to understand what it is you're going to be processing and what the trade-offs are when you're trying to do real-time data processing on streams of data. Right, so Storm is one of the oldest ones. It's been developed at LinkedIn. At Twitter. Actually, Storm has been developed at Twitter like 5 or 6 years ago, and it's been the underlying framework for all of their real-time processing. So every time you go and do something with a tweet, and all the processing in the background happens on a Storm topology, which does a lot of processing. And they recently came out with Storm 2.0, which is a new project called Heron, which is basically almost the same thing, but just better implemented. Now, Spark is a process that evolved to replace Hadoop, because Hadoop is really very slow and disk-bound, and Spark does a lot of the stuff in memory. And in our case, we're actually going to be more focused on Spark Streaming, which is an extension to Spark, to the distributed processing engine, which can do this in memory in a streaming fashion, so it will continuously process new data that comes in. And Spark is very popular. It's a huge project, lots of contributors, and it's one of the really mainstream, very basic, solid tools to use. And the two on the bottom are relatively new, both Flink and Kafka. Kafka is a message queue. It's very solid, and everyone, or a lot of companies use Kafka, but not everyone uses it for processing messages, which is what I'm going to be talking about today. So if we go over to Microsoft, there is a very cool tool from Microsoft Research called Microsoft Orleans. Has anyone heard of Microsoft Orleans? Almost everyone. There was actually a very good talk by Sergey Bykov last year here about Orleans, if anyone caught it. It was really good. So Orleans is actually an actor system, right? It's similar to Akka or Akka.net. It's not actually a stream processing system to begin with. It lets you create actors, which is just pieces of user code which you can deploy, and they run within a system and can pass messages to each other. And it's very good for creating distributed systems, which need to be robust and scalable. But on top of Orleans, there is an extension called Orleans Streams, which does stream processing. Because if you look at message passing between actors in a system, it's very similar to how streaming data processing works, because the data processing model for streaming data is basically to build a graph, a directed graph of operations, and then you stream data into it from one source. Each one of the operators does something with the data and passes it on to one or more downstream operators. Each one of those does something else, and then eventually they all go to some kind of sync where it's either writes it to disk or it doesn't do anything. So let's talk about a practical example, right? And this is an example I'm going to show a bit later. We want to do we're building a startup, and we're going to do something no one's ever done before. We're going to do sentiment analysis on tweets. Because it's the hot new thing, right? It combines machine learning with IoT and 10 different other buzzwords, which will definitely get us funded. So we're doing that, right? So what do we need to actually do in order to get tweets in real time? And remember, there's 500 million of those happening every day. We need to bring it into our system. We need to store them. And remember, the Twitter feed is a unrewindable stream, which means if we miss a tweet or if we can't process it in time, it's gone forever. We can't go back and restream it because new tweets keep coming in and the API doesn't support rolling back. So it's very important to actually persist them very durably, as fast as possible, and then do all the other processing stuff we want to do with them. So we want to put those tweets somewhere, presumably in some kind of queue, a distributed queue, or maybe a database that can actually absorb 6,000 writes per second. So it's going to be scaled out to a lot of machines. And then we want to take all this stuff, take it out of our store, do some kind of processing on it, maybe enrich it with geolocation data, maybe enrich it, obviously do semantic analysis on the tweet, add that to the basic data, then enrich it with maybe data about the user, if we could do some kind of user tracking or profiling, put it all back into the data store, and then expose all of this stuff for querying. But then keep in mind, we have 15 billion tweets every month, and that's maybe 15 terabytes of data or so. So we can't keep all of this stuff in our database forever, right? We need to take that, offload it somewhere else, and then if we want to go back to last year's tweets and reprocess them, it's going to be in a different system which can actually process petabytes of data, whereas we'll keep, let's say, a month of tweets back and process them in real time, in a more real-time fashion. So for this, we need, as I said, some kind of tool which actually collect tweets. And if you want to mentally map this to whatever you want, like a website which has events and interactions with ads, you can do that, right? Instead of connecting to Twitter and streaming tweets from there, imagine that your users come to your website, they click something, it causes a server event, a post back to the server, and then your web application or a microservice or whatever it is has an event. It's a real-time event. You can't go back because the user isn't going to go back and redo the event again. You have to store it somewhere if you want to record it forever. Then you have to store it quickly, and hopefully your website is very successful, so there's millions of users doing it all concurrently. So there's a lot of events happening. Right, and we want to put all of them into a durable storage and then process them. So there are basically two types of processing we can do in real time. One is actually really real time, which means as soon as the tweet comes into our processing framework, we do something with it, and we can't rely on any kind of history or any kind of other data because every class or every user code in our system just has this one event to work with. So the most we can do is either count how many of those there are and keep local track locally, or maybe we can talk to an external store, maybe put it in a database or update a field in a database. That's pretty much all we can do with a single event. The other kind of processing we can do is micro-batching. There's obviously also batching, but batching is by definition not real-time, right? You can go back and look at all the tweets and calculate stuff. But as close to as you get to real-time, is microbatching, which is taking a collection of events all together, let's say 10 seconds of tweets or a minute of tweets, doing some kind of processing on them, and then extracting a bit more knowledge. For example, I want to know what hashtags are trending for the past minute, right? If I want to know what's trending, obviously I need more than a single tweet to work with. So I'm going to collect, let's say, a minute of tweets, which is going to be, quite a substantial amount. It's going to be several 100,000. And then I can do some kind of real-time processing. It's still close enough to real-time, right? It's a minute. Minute is, it's sort of on the edge of real-time. Then I can extract something that's trending, and then I can send this downstream from my streaming topology, and something will happen with it. Maybe we'll adjust bids on ads, or maybe we'll, whatever, send alerts to users saying that, this thing is trending. So those are the two models we can do. And the frameworks I'm going to be talking about, they all implement one or the other, right? Because it's a very different kind of processing engine, and you can't really combine them very efficiently. So Storm, Apache Storm, implements a very continuous model. You basically define a lot of classes, user classes. Which, you can think of them as actors or just pieces of user code. And each one of those classes represents a single operation. And it can receive inputs from a different one, or maybe from some kind of queue or a source. It can do something with that input, and then it can send the input on to the next in the chain. Right? And this happens in real time, and each one of them processes exactly one event at a time. Right? Obviously, you can store local store, because it's a user class, right? You can define any kind of variables in it, but if the application dies, anything that's stored in memory is going to disappear. So it's not actually a robust way to store local data. You do have to have some kind of external store which can store your state. And the reason it scales so well is because Storm will create a lot of copies of your processing class, right? So if you have a class which, let's say, calculates a sentiment on a tweet, which we will have in just a moment, we can't just run one of them, right? Because there's no way it can process tweets fast enough. We need 100 of those, maybe 1,000 of those to actually do the processing in parallel, right? And so we have some kind of, the framework itself takes care of distributing the tweets to the different instances of our processing class, and then collecting the messages from them and pushing them downstream to the next class and the next class, right? And Spark streaming is built on Spark itself. So it has its roots in Hadoop and MapReduce. So it does micro batches. It actually fools us into thinking it's real time by taking very small batches of data and then doing normal Spark processing on them, right? Doing normal MapReduce stuff, which takes all the batch, crunches it together, and then gets a batch of results and pushes it downstream. Kafka is a message queue. Originally, it only did messages. So if you think of, how many people know what Azure queues are? Azure queues, use them, right? Simple queues in Amazon, right? So it was kind of like that, right? Where you can actually just put data in, read data out. You can have a bunch of different topics you can read and consume. And eventually, the guys at LinkedIn who built Kafka left LinkedIn and founded a new company called Confluent. And they created a actual processing platform based on Kafka. And they have enterprise support, and they build a bunch of other stuff around it, which does more than just push messages around. It actually processes messages. You can create basically the same kind of topology for processing messages as you can with other frameworks, and we'll show that in just a bit. And Flink is actually very similar conceptually to Storm, where you define a bunch of actors which will process your topologies. And then we can talk about how you do that. Like, let's get to the actual code, right? Let's look at some code. So there's two ways to do this, right? There's two ways to actually declare how our processing framework is going to work. We can have a declarative style, which looks very much like Link in .NET. Everybody knows how Link works in .NET? Pretty much, yeah? So you actually, and Link, by the way, is an excellent example for stream processing, right? You can have an infinitely large enumerable, and you can do some kind of processing. And if anyone know how plink works? Plink, yes, parallel link. There's like one guy saying, yeah, I use it every day. So you can actually do the same kind of declarative processing in parallel. And if you take that and you can think of it as doing the same thing but on multiple machines, that's basically what stream processing is when you do it declaratively. You take some kind of streaming source and you transform it in different ways. For example, this is a very simple example, which is like the hello world of the big data world, which is word count. You take text and you count how many of each word there are. This is basically the equivalent of writing hello world when you learn a new programming language. So we take every string, we split it into words, and then we map every word to a count, which is 1, and then we reduce them, we count how many of each word we've seen, right? And This is actually very concise syntax. And for simple things, it works very well. For more complex things, it doesn't work very well because, for example, maybe instead of just counting words, what we want to do is go and update a database. Right? So in one of the steps, we can take an event in, and we want to go and update a database. It's not really something you can put in a single line in a processor. Right? And then, so you can use a compositional API style, which lets you actually define user-created classes, which just all share some kind of common ancestor. In this case, the example on the left is from Storm. And Storm uses a metaphor of spouts and bolts. They have a thing with water going on. So a spout is the source of your data. It's a class which just takes the data from somewhere and sends it downstream. And every bolt in the chain does some kind of transformation. So you can have a bolt which just prints out the data it receives, for example. So it doesn't produce any data, it only consumes data. Or you can have a bolt which takes in a sentence, it splits it into words, and it sends each word out. So it takes a small stream and it expands it into a longer stream of multiple words, right? And then what we can do is declare a topology, a graph of these components. So we can take 3 bolts, and we can say this is one sends data to the second one sends data to the third bolt. And then the spout will start sending messages into the bolts, each one will do their thing, and the whole topology will work. And obviously, we will have multiple copies of which bolt, which is how the whole thing scales. Right, and most of these tools are unfortunately written in JVM. So unfortunately, because I'm in a mostly .NET conference. In a Java conference, I'd say luckily they're all written in Java or Scala. Yeah, this is the unfortunate truth of the big data world. Most of the tools are written in Java, and there are very few Microsoft-ish or JVM-related tools. So they all support JVM. Some of them actually support Python if you want to declare your code in Python. And Orleans is basically the only example we can point to and say, Microsoft have done something in this. And we'll talk about Orleans. I'll show an example of that in just a minute. So let's look at some examples, right? Let's look at actual code, because it's early in the morning. Everyone's still fresh. We can look at code, right? So let's look at code. And we'll start with Storm, because Storm has the simplest API and most expressiveness. So we can actually demonstrate it in the easiest way. Excellent. All right, so let's go to our Storm topology. There's going to be some Java. If you can just mentally pretend it's broken C#, everyone's going to be happy, right? This is kind of like Russian speakers feel about Ukrainian and vice versa. They can kind of understand each other, but they don't want to admit it. All right, so what we're going to do is, as I said, the simplest thing, we're going to count words. It's not exciting. We're going to do something more exciting in just a couple of minutes. But for starters, we'll do something very basic. So we're going to have a spout, a Storm spout, which is just a class that sends out a bunch of text, and we're going to count how many times we've seen every word. It's a contrived example, but it demonstrates what we're talking about very easily. All right, so the Storm topology yeah, everyone can see it, especially in the back, because it's a very weirdly shaped room. All right, good. So actually defining our processing topology in Storm is very straightforward. What we say is, in our topology, we're going to have 3 components, 3 bolts, right? We're going to have, and 1 spout. The spout just generates random text, random sentences. We call it a spout, and then we start connecting processing classes to it. We have a class called split sentence, and I'll go into it and show you the code in just a sec, but the name pretty much says it all. It takes a sentence and it splits it by spaces, right? And we connect it to our spout. So anything that comes out of the spout will go into our split sentence class. And notice that we're actually going to be running, this is the parallelism. We're going to be running 8 instances of this class. So we have 1 million messages coming in every second. Is going to be split between 8 different classes. And those will almost certainly run on different machines, right? So we need to spin up a whole cluster of Storm machines. And I'm not going to bore you with how it's actually done in the engineering sense, but it's not easy, I'm sorry to say. But it's much easier than writing it all on your own, which is the point. So we're going to take the split sentences, which means that our small string of sentences, a stream of sentences, is going to actually expand. Every sentence is going to turn into a bunch of different events in the stream. And we're going to split those and send them to the word count bolt, which actually does the actual counting and stores the state of how many times it's seen each bolt. And the important thing here is we're going to be shuffling it, not just randomly. We're going to be consistently sending any particular word to a particular instance of this bolt. right? So if the same word comes up, it will go to the same instance of a bolt, so it will actually be able to count it, right? Because each bolt, we'll see in a second, internally is thread safe, but if you send the same word to different bolts, each one will have a partial count, and that's not what we want. And from there, we just send the actual count to our printer bolt, which all it does is print. It doesn't actually emit anything. It only collects data. So let's look inside the split sentence bolt just so we can actually see how it works. The bolt itself is a very simple class, right? It's a class which extends some kind of basic Storm class that Storm knows how to run, and has exactly one method that you can run. It's called execute. It gets an input, which is a tuple. It's just a class with a key and a value, right? And it has a collector where you can write output. And you can write as much or as little output as you want. It doesn't have to be one-to-one. So we can get a tuple, which is a sentence in as the input. We split it, and we get an array of words from that sentence. And then we emit each one of those as a new tuple, right? So it's very simple. We got a sentence in. We get a bunch of words out. Done. This goes into our actual word count bolt, which, again, doesn't do anything super complex. All it takes is every tuple. And again, in this case, it's not a sentence anymore. The word count bolt actually gets single words. And it just has a hash map, which is a dictionary for you C# speakers, where it just updates the count of how many times it's seen the word. And as you can see, the bolt itself is entirely thread safe. Right? We're using a local variable. We're guaranteed that this thing is going to always execute on the same thread. There's no way to call this exact code concurrently. So Storm actually guarantees a very simple programming environment for us. All the stuff you know about how you need to do locking and thread safety and all that, we don't need to worry about any of this because the framework takes care of the actual execution environment, and we just need to provide the user code which does the actual operations. And that's extremely convenient, especially when you start thinking about how you're going to synchronize concurrent code across a cluster of 100 machines, right? So the fact that all of these frameworks actually take away the concern for threading away from the developer is extremely convenient, right? So all we do here is we collect all the counts, right? And then we emit the actual count itself. So instead of just emitting the word, we emit a word and a number of how many times we've seen that word, right? Now this is obviously very unsafe. Who can think of why this thing is actually a very bad implementation? It's very unsafe. Anyone? It's not a trick question. Let me give an example. What happens if we shut down one of the machines in our 100 machine Storm topology? Again, not a trick question. It's just what happens if we shut down the machine? So any instances of this bolt that we're running in the memory of that machine, we're going to lose, right? So we're going to lose all the state, which means the machine will actually, even if it's shut down, Storm will redistribute the bolts to different machines. Storm takes care of all of that stuff, but every one of those will get a fresh new instance of our bolt, which has no state stored. It will just start counting from 0. Right? So we'll have some words with an existing count and some words with a new count. So this is why, in this case, we'll actually have to manually take care of state. And usually the answer to that is put it somewhere else, right? Where do you put state? In database. Anyone said database is exactly correct. Database is the place to store external state. Obviously a fast database because SQL Server probably isn't going to run at 100,000 events per second or anything. All right, so the printer bolt actually does exactly what it says on the cover. It does exactly one line, so we get a tuple and we print it. That would be the equivalent of console write line in C#. I know I didn't have to translate it. I just like it. All right, so let's run this and see if we get some word counts. Right, so we can run the topology itself. Now, I will run it locally, but in a real production environment, there's actually a cluster of Storm machines running, and they're doing nothing at the moment. They only start doing stuff when you create a topology, which is just a library you compile and build, and you submit your library with your user code to the Storm cluster, and then it starts executing all the stuff you defined. Right? Because normally when you spin up a Storm cluster or a Spark cluster or any of these things we're talking about, it's not actually doing anything because it has no user code to execute. You have to submit the user code and it will get executed. So let's run this. And unsurprisingly, it will spin out some text and we'll see that it actually produces counts for different words. So the example itself is not very interesting. It spins up a bunch of different stuff in the background because, again, the clustering, even if you do it locally, is very complex. But then we start seeing a bunch of word counts appear. And if we pause this for a second, we can see that, yes, indeed, it's actually counting words. So let's see we had at at 42, and then a second later we had at 43, and it will just continue accumulating counts for every word. Now this is obviously not useful for anything, but if you just mentally map this to something useful, like let's say you're doing anomaly detection, and you're listening to your company network, you're attached to Active Directory. This is a real example, by the way, from a company I worked with. They're attached to the Active Directory events. They're scanning all the login events, all the network access, anyone who opens a socket or calls the URL on the front end. And they're counting how many times any IP has tried to log in or access a computer. And they're looking for anomalies in their behavior, right? So they're counting how many logins for every machine, for every IP happened. They're storing it in a separate database. And anytime a logging happens outside of normal parameter, for example, an IP which only connects during the weekdays, tries to connect during the weekend, that will cause an alert. And it's all implemented as a storm topology with a bunch of rules and just counters which count how many times everything happened. And it runs on about 10 different machines because they're processing a lot of events for a large customer. And this works very similarly to this, just a little more complex in the actual execution logic. All right. So let's switch over to Spark, which is an entirely different concept. Spark actually, as I said, came from was born out of Hadoop and the need to run very large batch processing operations in parallel. And then what happened was they took that concept and mapped it onto micro batches. So it became much more real time. And Spark actually, let's run this. Spark works in an entirely different way from Storm. First of all, you don't declare workers. You actually declare your logic as a logical expression, kind of like Flink, kind of like the way Java streams work. So in this case, we're creating a stream of data coming in from a socket. Just to spice it up, I'm going to just type in text. It will listen to sockets on port 1111, and it will count the words coming in from that in real time. And the logic itself is exactly the same as we saw in Storm, right? We're doing word count. So we have our stream called lines, and we flat map it. Same thing as we would do with .NET or Java or anything, any framework which supports logical expressions. We flat map it by splitting the string itself by space. So we turn the small stream into a larger stream of words. Then we map every word to a count, and every word only has a count of 1. And then we reduce the stream, right? We aggregate the stream by word, and then we get the count of how many times we've seen every word. And the important thing is, you can't do this infinitely, right? Because then it would never finish, right? You can't just, because the stream would actually wait for the data to finish before it can aggregate and reduce it. So we have to define some kind of window of how long to wait before you actually run this calculation. And it will continuously run the calculation in intervals. All right, so we create the stream with a 5-second window. All right, so every 5 seconds, it will take whatever it accumulated until then. It will execute the count logic and split it and all that stuff, and spit out an answer. And this answer can go somewhere. You can go into a database or some kind of other storage, or it can go and be the basis of a different expression, which does something. So let's run this and see if it actually works. Well, yeah, there we go. So it'll actually just listen for connections on sockets 1111. And there we go. Let's go A, B, and C. And we should start seeing counts every 5 seconds, right? And as you can see in the background, you can't see anything in the left corner, so let's move this. Let's move it over here. And this over here. There we go, much better. So you can see that it spits out aggregations every so often. And if I actually give it some text to collect, in the next 5 seconds, it will count the letter B 3 times, right? And if we do this and continue just doing stuff, it will spit out intermediate counts, right, every 5 seconds. Now this is actually, the main difference between the two approaches is twofold. One, they have different latency and throughput. Right? Storm has much lower latency because as soon as an event comes in, we run it through the entire topology, we do all the processing, and we get a result immediately, usually within milliseconds. And there's monitoring that can actually tell you how long the processing takes for a single event. With Spark, the minimum latency obviously is 5 seconds, right? We can't get a result in less than 5 seconds. or an average of that. Let's say if an event comes in, on average it will wait 2.5 seconds, right? But because Spark can batch results, it can reuse a lot of internal mechanisms for threading and memory allocation. It can process data a lot faster at scale. So if you need to process 1 million events, it will be much more expensive to process them one at a time in Storm, even though every result will come back quickly, than in Spark, because it will take the whole million as a batch, do processing in the background, and spit out a result. So Spark will actually have, Spark Streaming rather, will have much higher throughput per second than Storm, and this trade-off is what you have to play with, right? And companies which come at this from fresh, right? They have no streaming topologies, they have no data processing, and they're building something which needs to handle all the traffic that's coming from their event source, whether it's a website or a mobile application that's sending back telemetry or whatever. IoT is very hot right now, and obviously you have something which produces events on the edge device, sends it back to the server, and then you have to do something with it, right? You have to do some kind of cool machine learning stuff to serve ads to the user, obviously, because again, that's what the internet is all about. And one other thing which I'm not allowed to say. But the difference is, again, if you need real-time processing, you go with something conceptually built for processing single events at a time. If you need something just high throughput and you don't care about latency as much, you go with Storm, and you have the two approaches. And all the other frameworks, they fall somewhere on this continuum, right? We'll look at Kafka, which is also like one event at a time. We'll look at Flink, which does batching, and they're going to fall somewhere in the middle. All right, so let's look at what do we have next. Let's look at one more thing with Spark, which is very cool, and that's Spark SQL. On top of the normal Spark execution engine, we can actually run queries. Spark has a language called Spark SQL, which lets you actually run queries on top of your stream in real time, right? Because you don't have to have just one stream, you can have multiple streams. For example, let's say I have a stream of user events coming in from my website, and I have a stream of GUIPs or something that provides extra context for every user. I can take both streams in Spark and I can join them, right? I can take for every user or for every IP in the user stream, join with the matching IP and the location from the geohash stream, right? And the stream can actually be entirely cached in memory, and that's what Spark will do. And we can actually go and just use a regular SQL expression to join the two streams in memory. We can do the same thing with Storm, for example, but then we'd have to manually write the join logic, which is a bit more complicated. So in this case, we have exactly the same thing. We have basically the same local host. We connect to the socket. We listen for words. And then instead of batching them, what we do is we store them in memory every 5 seconds, and then we run a query on them where we do where we define a schema on our data. And the schema is very simple, right? It's a table with two columns. We have a column called word and a column called count, right? And then we just select from a column called word, and the count is always 1 because it's a single word. And then we just run select word and count of everything as total, right? As we would in a SQL query. And this will actually run every 5 seconds and take the aggregated data and run the query on the aggregated data every 5 seconds. So if we run this, we'll see that it does basically the same thing I said. Let's open our socket and listen to it. And it takes a while to spin up because all of these frameworks actually have a bunch of stuff happening in the background. And then if we run a bunch of data, we'll see that now we have A1, and in the next 5 seconds, we'll see all the other letters I typed again. And now we can actually see them as a SQL table, right? And we can do SQL operations on those, which is very convenient, especially when you are trying to do complicated analysis on them. All right, and Flink works more or less the same. It works like Storm, where you define bolts. They call them differently, but it's the same idea, where you define operators, you connect them in a graph, one pointing downstream to the next, and you run your data through them. The main difference is Flink comes with a bunch of different libraries which lets you do complicated stuff on top of the streaming stuff. For example, Flink comes with a library for CEP, complex event processing, where complex event processing deals more with finding patterns or doing more complicated queries on top of your streaming data. As an example, let's say we have our word stream coming in, letters A, B, C, and so on, and we want to look for patterns. I want to find every pattern where the letters A, B, and C repeat within a certain time frame. And if you think about this and look at actual real-world examples where this originated, think of, for example, stock trades. You have a stream of stock updates coming in all the time, and I want to look for patterns where a certain stock behaves in a way. It goes up, and down, and then you expect it maybe with some probability to go up, right? And if it behaves this way within a certain time frame, maybe you go and you adjust some positions and buy the stock before it goes up again. And again, we're talking about microseconds here, right? Because we want to adjust positions within microseconds, buy the stock, and sell it a microsecond later if it goes up by a micro%. Or you can think of other things like user behavior. Again, the same thing with tracking user threads within a network. If you want to look for a certain pattern of events and identify them as a threat, right? We want to search for patterns where someone tries to log in and fails 3 times, and then immediately the same IP tries to log in with a different username, right? So anytime a pattern happens where one username fails 3 logs in, and then the same IP logs in with a different username, we push out an alert, right? And you can also do this manually. You can implement this logic manually, but it's very convenient if you can just define the pattern and listen for it, right? And Flink does the same thing, right? We can see where we have exactly the same thing we had earlier with the word tokenizer. We take in text, we tokenize it by lines. Same thing we had with Storm, but in this case, we define a pattern and listen for that pattern in the stream. So we want a pattern which starts where the text is equal the letter A. It has to continue and be equal to a letter B, and there can be other letters between those, right? Because we're listening for a whole stream, but we want A and then B, and then we want C to appear within 1 second, right? And if it's more than 1 second, it's not interesting, but if it appears within 1 second, that's part of our pattern, and we want to listen to it. And then we do something very interesting, because Flink lets us actually connect to its internal state externally. It has a RPC mechanism where you can connect from outside the topology and ask it questions, right? Which is very interesting, because then you can look at your stream processing topology as kind of a microservice, which can serve requests. Right? I can always turn to it and say, what's the latest pattern, or what's your current internal state? How many users have you counted? Right? And then instead of just having a very closed processing system, we have something that can serve intermediate data externally. And we'll actually see an example of that in just a moment. All right, so let's run this. And again, same thing we had earlier. Not you. I meant you. Open a socket, run this thing. And now it will actually listen for events coming in on port whatever. There we go. And if I just put in, all it does is print out the letter. But if I happen to print in the exact pattern, it will find the pattern, right? And if I do this in any sort of order, it will still detect the pattern within the stream, right? And if I wait more than a second between B and C, then that's not part of the pattern, obviously, right? So if we do several of those, we'll detect 2 of them, right? So now we actually have the ability to not just take our events, but actually do some very complex processing that's declared in a very straightforward manner, right? You don't need to go and write some kind of logic which aggregates and keeps state in memory, because state, as we saw, is vulnerable to failures, to network failures and machine failures. So it's very hard to store state, and it's very convenient when the framework does this for us, right? So let's move on. Let's move on to our last contender, which is Kafka. And Kafka is interesting for 2 things. One, it started out, as I said, as a messaging queue, and then they tacked on the ability to actually execute code on the events in real time later. And 2, they've completely separated out the runtime environment from the actual processing environment. One of the problems with all of the mechanisms I talked about, right, Storm, Spark, Flink, all of these, is they implement their clustering solution on their own. Right, so they have to do a lot of work, and they have to build a complex system which will do all the scaling and processing and failover and load balancing between different classes in the topology. And essentially, it breaks the single responsibility principle by having a system which both runs user code and manages resources, and it tries to figure out where to run every piece of code, where it's efficient, where it has resources to spare, and do all the self-healing. Kafka, either by laziness or by lack of resources or by design, have decided not to deal with any of that, and they've separated out the execution part from the clustering part. A Kafka Streams application just uses a library which handles all the logic of connecting to a Kafka topic, a Kafka queue, reading messages, processing them in the application, and putting them in a different queue. It does nothing to say where the code will run. It's just a Java application, or you can actually implement it in Go. There's a Kafka library for Go and for .NET, as it happens. And it's your responsibility to create copies of this application and to run them, which lets us do very interesting things with scaling the application, because it's up to the actual organization who uses them to scale the application. So for example, anyone who's using currently Kafka Streams most likely uses some kind of orchestration. So whether it's Docker or Kubernetes or one of the orchestrating frameworks which let you run a bunch of copies of our application, and every application internally uses Kafka Streams to coordinate and read messages from Kafka, process them, put them in a different Kafka queue. Right? So separating out the actual execution from resource management was actually a very wise decision for Kafka, because it both let them write less code and simplify the execution, and also give the control of where to execute code to the actual user, which lets you avoid trying to set up a very complex system. Right? Spinning up a cluster of Storm or Spark is just a daunting task on the engineering level to connect and configure everything correctly so they talk to each other. All right, so let's look at Kafka before we move on. And it's the same exact example, only we're going to improve something this time. Instead of printing out the counts, we want to expose it as some kind of API that you can query and get the current count externally, right? And you can start thinking of stream processing as kind of a small use case of microservices. Everyone knows about microservices, right? It's the new thing. Everyone's doing microservices, even if they don't have to. So you can think of it as a microservice, right? What we're going to do is the code itself that does the processing is a microservice, except now instead of getting web requests, is getting events as requests, does some kind of processing, and puts the response asynchronously somewhere else. And on top of that, it keeps state, which we will expose as an actual microservice with a REST API and everything, so you can query the external state of our processing. Right, so we're going to be counting words, because again, stupid example, but it's interesting from an engineering point of view. And then we want to expose the count as a REST service to anyone who wants to query it, instead of just printing it out. All right, so let's take a look at that. This one. All right. So our Kafka application is exactly the thing we had earlier, right? It takes messages. Don't have to read the code. I'm not there yet. But what it does is it takes messages from a stream, from a Kafka queue, in fact, and anyone can put messages into a queue, right? They can come in from anywhere at all. It takes messages from one queue, counts how many words there are, puts them in a different queue. But you can look at a queue, or rather at a stream, as a very large changelog of a table, right? There's actually a duality between a changelog or a stream and a regular table, a key value table, right? Because what's a database table? It's just the current state of all the changes that accumulated so far. So let's say we're counting words, and we only have 2 words in our dictionary, A and B. At a certain point, we have A1, then you have B1, then we have A2, and A3, and so on. If we look at this from a stream point of view, we'll see a bunch of A's, and we can count all of them. If we coalesce this into a table, we'll just have a table with two items, A and count 4, and B and count 1, or something, right? So you can always expose the current state of a stream as a table, and then you can query this table to get a real-time look into what's going on in the stream. Right? So this is what Kafka actually does, and it lets you both process a stream and expose it as kind of a virtual table on top of the stream, which just deduplicates all the values and gives you the latest snapshot of every value. So as I said, all it does is exactly as we had earlier. Let's look at this. It takes a bunch of text lines from a queue. It splits them and it splits them by spaces. It flat maps the values into words in a longer stream, and then it just groups them by the key and the word, right? And then it prints out the counts into a topic called something else, right? So this part is not interesting. We've seen it like 5 times so far. But the interesting part is we can actually now spin up a REST service. I'm not going to show you how to spin up a REST service in Java, because if you have to do it, you already know, and if you don't, well, you're in luck. And you're going to live much better lives and happier not to know how to do REST services in Java. But basically, we spin up a REST service which can respond to requests, and it has a very simple API. You can go to /count and the word itself, and it will tell you how many times it has seen the word. Right. So if we run this, we'll need to produce some words. Let's run the example. We'll produce some words. Let's see, A, B, C, A, B, C. Just enough, I think. If we read the topic, we can see that we'll actually have a bunch of words, right? So now if we read it, and it's all from the command line, because that's the way Kafka operates, it's going to have a bunch of words in it. But now the interesting part is we have a REST service on top of it listening to how many events we had. So if you go into our web API, we can call it and get a response and say that we have A 25 times, right? And if we go and look for the count for B, there's 10 Bs, right? So now we can actually take a stream topology and process a lot of data in a very scalable manner. We can process, thousands or millions potentially of events per second. And if we store state, we can now query this state as an application. And this is the direction a lot of streaming frameworks go towards, where they can let you actually build applications on top of your stream processing topology and expose them as services that someone else can consume. And this, first of all, in this case, we've just replaced the database, right? If we can query our streaming topology directly, we don't need to put this data in a database. We actually eliminated one very complicated component from a complicated system, because we can actually now talk to our data directly and get a snapshot right away. And also, we actually have a much more real-time view of what the data is doing, right? Because it updates in real time. So now let's look at a much more interesting example where we're going to actually do what I said earlier, and that's we're going to take tweets and we're going to analyze them and do some sentiment analysis, and we're going to store them and do a dashboard that shows you tweets in real time. And I have exactly 10 minutes to do this, so hopefully we'll make it just in time. And I'll tell you, it took a bit more than 10 minutes to actually set up this demo, but not by a lot. Right, because you can connect all these things like Legos. So let's look at our example. And I purposefully mixed and matched different frameworks here. Obviously, you would never do this in production. You'd use just a single framework. But what I'm doing is I'm going to be using Storm to read tweets. Spark to read tweets from the Twitter Firehose. And Twitter, by the way, has been just a massive boon to anyone who's doing demos, because it's the best source for streaming demos you can have. Right? You can just get data, and it's free. As long as you have an internet connection, you can get it. The problem with it is you have to provide some keywords to filter the tweets. And I've tried a lot of keywords, and most of them don't produce any tweets. But I finally figured out the keyword which produces the best tweets, and it's Trump. And I have no personal stake in the election in the US, but they've been great for my demos. So we're just going to find a bunch of tweets with obviously politically loaded keywords, because it gets you a lot of tweets, and most importantly, they're beautiful for sentiment analysis, because there's a lot of emotion and sentiment in political tweets. So all we do is we actually use the built-in plugin for Spark Streaming, which knows how to connect to Twitter and actually stream tweets to you. And we're going to be doing two things. We're going to aggregate them by window, by about 10-second window, and count hashtags and find the most trending hashtags every 10 seconds. And then we're just going to take all of the tweets, throw out most of the data, save about 6 different fields as a JSON object, and put it in a database. Why in a database? Well, I work for Couchbase. I have to plug Couchbase somewhere in my demo, at least once. I think it's in my contract somewhere. And also because we want to query them, right? And I've shown you how you don't have to use a database with Kafka, and now I want to show the other way where you can actually put this in a data store and query it as a regular database. And then we'll take all of this data, do some sentiment analysis on it, and put it in hopefully a real-time updating graph. So let's run this. And by the way, you really, really shouldn't. It's going to show all the tweets on the screen. Please don't read them. They're terrible tweets. Just don't. I've made the mistake of reading them because I was trying to find the ones with the most positive and negative sentiment, and it ruined my life, basically. All right. So we have tweets coming in. If we go into our database, we'll see that we are indeed getting tweets. Let's look over here. And yeah, we get tweets like this. Something, something. What we're interested in is text. Right, so now what we want to do is actually take these tweets, do some sentiment analysis, enrich them with data, and then put them back in a database so we can query them some more. Right? Now, why don't we do this first before we put them in a database? Because the processing might be very complex and might take a lot of time. And as we know, tweets aren't rewindable. If you lose the tweet, if the processing framework fails, and before you store the tweet, you're going to lose it forever. So the first thing we want to do is store it durably, and then we want to do all the other processing stuff. So you can either put them in a queue like Kafka or Amazon Kinesis or something like that, or put them in a database. And then we stream them from that place and do all the processing and stream them back. So to stream them back, we're going to use Storm, because why not? But we can do either any one of those frameworks. In this case, we have a very simple topology. We have a spout, which streams data from, in this case, Couchbase, the database, but it could be Kafka or any kind of queue. It filters out anything that's not a tweet, just so we don't put garbage in a database. And then it calls the sentiment bolt, which takes a tweet, calculates the sentiment score, and attaches it, and then stores it back in a database. So the sentiment bolt itself looks very simple, like this. There it is. All right, it takes a tweet. It uses the Stanford Natural Language Processing Library, which is free and open source, and you should definitely play it if you're into that, which calculates a sentiment score from 0 to 4. 0 is very negative, 4 is very positive, and 2 is neutral. And it just gives us an integer, right? And then we attach this integer back to the JSON object and store it back in a database. So now some of the objects will start getting sentiment scores. And we now have actually two streams running in parallel. One is storing tweets, and the other is trying to catch up and attach scores to every tweet, right? And because calculating scores is much more complex, the streams are actually going to run at different speeds, because storing tweets is very easy, and calculating sentiment takes a lot longer. So the second stream, the second processing, is what we need to scale out to many more machines if we want to actually catch up to the first stream, which is just saving tweets. So let's run this. There we go. And it will now start actually reading all the old tweets, right? Because we started saving tweets like 5 minutes ago. We have a backlog now. We can chew through the backlog, and then we'll get to real time and start getting the real-time tweets. And it's going to spin up and do a bunch of stuff. And now we can go into our database and actually do some queries on the tweets, right? So we can do something like select from tweets. Right, so let's say what the average sentiment score is for regular tweets which don't mention Trump. And if we look here, we can see that it is, in fact, let's expand this a bit. I think my computer is about to explode. I'm doing way too many things all at once here. All right, it's about 1.3, which is on the negative side, but it's somewhere between negative and neutral. And if we just change this to, or I have to stop this because things are going to explode. As I said, natural language processing takes a lot of CPU power, and that's the part we need to actually scale. So let's stop this, and then go back to our querying. Okay. It's going to respond eventually. There we go. Now it's better. All right, so let's run this, and we can see that if we do include those, then the tweets are obviously much more negative, which really shouldn't come as a surprise to anyone, but it's interesting to be proven right. All right, so as it happens, and we don't have a lot of time, so I'm not going to show you how, but I'm also replicating tweets in the background from my data store to Elasticsearch. Who's heard of Elasticsearch? Hopefully everyone, like half the room. Okay, good. Elasticsearch is an engine for doing full text analysis and real-time queries on data. And it has a plugin called Kibana, which does real-time dashboards really nicely and very simple to set up. So in the background, I have a job running and replicating data from our data store to Elasticsearch. And I've set up a dashboard in Elasticsearch to actually show our tweets on the map if they have a location, and show the number of tweets on a nice histogram, and the graph of sentiments and the top most prolific users. And this is just by way of showing an example that streaming frameworks are actually excellent ETL tools. Right? You can stream data from one place, do some kind of transformation in real time, and stream it to another place. Every framework that I know of has at least 3 common plugins. There's a plugin for reading and writing data to HDFS, Amazon S3, and Elasticsearch. Elasticsearch is always in the top 3 things where you want to put your data. Right, that's the first thing most framework builders actually implement. And as you can see, tweets are still coming in. Right, we have showing tweets for the last 15 minutes, and it refreshes every 5 seconds. And you can see some of the tweets happening in, and we have bars coming in, and the sentiment graph has stopped. It's not actually moving on because I stopped the topology which calculates sentiment, but the topology that brings in tweets is still going, right? And I can now go back and rerun the sentiment analysis. And this is one of the benefits of persistent queues and persistent stores, that I can go back and actually change the way I calculate things in parallel. So let's say we have the sentiment topology running all the time, and I change the algorithm. I now calculate sentiments differently. But I don't want to stop showing my graph right now. I want it to keep running, and I can spin up a second copy of the topology with the new algorithm and run from the beginning of my log over all the tweets, stream all of them from the beginning, recalculate, and when the second topology catches up to the real time, I can turn the first one off, and then I will have seamlessly actually transitioned from one type of processing to another without any downtime and without losing actual real-time data. Right? So in this case, as you can see, the end of this graph is actually moving further in time because we stopped processing it. All right, I'm done exactly on time, which is a new thing for me, because I like demos, and I have a lot of demos. Hopefully you've learned at least something interesting, and thank you very much for coming, and enjoy the rest of the conference.